and this guy is a 1 ohm. And my whole job here is to calculate this current right here as a function of time. Now, I want to remind you here that this is a second order differential equation. This is kind of a nasty one, right? You get a natural response, but we're going to ignore the natural response because we're going to assume that it goes into steady state, which means that the natural response is decay. So all we're looking for is the force term. And if you look at the force term, it has to have what? B1 cosine of omega t plus B2 sine of omega t. And you know that that takes a lot of work. But baby, let's look at it with phasors. Right? Let's look at this thing with phasors. Let's see if we could rock this baby. Okay? Any of you guys watch the basketball game last night? LeBron James, man. Okay, here we go. Check it out. Look what I'm going to do. Phasor circuit. So what do I have to do to a phasor circuit? I got to convert the inductor and the capacitor into phasor form. Here we go. So let's look at that. XL. XL is going to be what? Omega L. Where's omega at? There she is right there. Right? It's 3 omega. Omega is 3 rads per second. What's the inductance value? 1. So what is this guy equal to? 3 ohms. Let's do the exact same thing with the capacitor now. The capacitor now has what? XC is omega times C in the denominator. Let's put her in. So if I put her in here, omega is what? 3. The cap is 1 over 12. So if I bring the 12 up to the top here, I'm going to get 4 ohms for XC and 3 for XL here. What's my phasor circuit look like now? So in phasor form, it goes like this. So now, here's my phasor circuit. So my phasor circuit says that I have 1 volt. Do you see any phase here? No. Because there's no phase there, I put 0 degrees. Typically we don't put any 0 degrees, but I'm just putting it there to be as clear as possible. There's my source here. Where's my resistor? This guy's a 1 ohm. Then I have my cap. I got to put in my minus J value here, so I got J 4 ohms. Then I got my inductor, and this guy's going to be J 3 ohms. So how do I calculate this guy? The way I would calculate this guy is that if I want this current, right, if I want the source current here, right, that's what I'm trying to calculate. We know that the source current has to be what? I source has to be the voltage source divided by the equivalent impedance. Now, if you look at this guy's in series with these 2 guys. So what am I going to do? This equivalence means that I got to sum these guys up. How do I sum them up? Here I go. This is in series with these 2, so then I'm going to write 1 plus these 2 guys in parallel, which will be minus 4J. Oops, you know what? I forgot the J on that one. So I get 4J parallel to J3, all over 1 volt. So what I'm going to do here is that I'm going to clean this guy up right here. If I clean this guy up, this will be minus J4 times J3 minus J4 plus J3. You can see that the J and minus J cancel out, right? That gives me 1. So I get 12. Then I look at this guy here, and I see that it's minus J4 plus J3, which gives me minus J. I bring up the J, right? I bring up the J, and then I have J12. So, when I look at this guy here, I'm then going to have 1 volt divided by 1 plus J12 ohms. I'm not done yet, but I'm at the edge, so I've got to move that way. So then what I'm going to do here is that I'm going to put it into polar form. We want everything in polar form. By the way, I will not try to do something crazy on the exam. No interest in that. Okay? No interest. No interest in that. All I'm trying to do is just get you to the end. That's all I care. So let's look at that. So then the current is then what? 1 plus J12 over 1 volt. So what do I got to do? I got to convert that guy into a vector. So here I go. So this guy has to go into polar form. I want polar form. So how do I do that? There we go. So what's the magnitude of this guy? It's got to be 1 squared, 12 squared, 145 squared. Okay? What's the angle? The angle here, theta, has to be the tan inverse of the imaginary part divided by the real part, which has to be 12. So did I calculate these guys? No, I didn't calculate it at the end. Okay? So now this is in polar form here. So if I calculate this in polar form, what I end up getting here is that this now is 1 volt, and let me call this Z, and this, of course, theta right here. So then I have Z e to the J theta. And I'm going to get a positive value for the angle. So then when I flip it up here, right, so this guy's really 145 square root, and then the angle here is what? The tan, actually, did I calculate the angle? I hope I did. Yes, I calculate the angle is 85.2. That's the angle right there. Remember, how am I writing this angle? E to the J, 85.2, is the same as 85.2. Okay? It's exactly the same. So if I have this in the denominator, look what I'm going to do. I'm going to take this guy here, and that angle goes where? Upwards. And so that J in the denominator becomes negative J. So then this guy becomes 1 over the square root of 145 times E times negative 85.2 degrees. And so now this guy is my phasor current right here. Okay. Let's say I want to put this in the time domain frame. Okay. So if I was, so in the time domain, the solution looks as this here. So I get IS, and then I'm going to write this in detail now. So I'm going to get 1 over the square root of 145, e to the minus j, 85 plus j, sorry about that. No, it is minus. 2 degrees here. Okay? So now I use Euler's relationship. Okay? So here, so now I use Euler's relation. And if I use Euler's relationship here, note that this is what? 145 square root cosine of minus 85.2. Oh, I did something. I have to come back. I can't use Euler's relationship. Let me tell you why. This is our Phasor solution. Okay? This is our Phasor solution. But remember, what kept canceling out in the equation? E to the j omega t. So now if I want to transform back, I have to add, right? I have to come back in here, and I have to add by hand e to what? J omega t. I have to do this by hand here. Okay? So I add by hand. So now that I add this by hand, what does this mean here? What this means here is that this guy now, if I now use Euler's, what I get here is that IS is then going to be what? I can combine these guys, and this guy is going to be 145 square root, and then I get cosine of what? 3t minus this guy, which is 85.2 degrees. And then I get the complex part, which will then be, again, 145 over sine of 3t 85.2 degrees. So to get the time domain, I then take the real part of IS, and the real part says that I focus on what? This piece right here. So what do I get? The real part, which will then be the current. If I was to solve the differential equation, I would then get 145 times cosine of 3t minus 85.2 degrees. And now, you got to ask yourself. Now, I agree that right now this is challenging because, I mean, what are we doing here? We're doing new stuff here. But I want you to think about it for a minute. If I gave you this, you would then launch into a differential equation. And you have to worry about initial conditions and all of that. But now, look at this here. I went from here to here. How long did this take to do? Not that long. And then if I put it into this form and I get it here, now note, you weren't like really new to this. I mean, you're really new to this, so therefore you'd probably struggle with this a little bit. But if you had just a little bit of practice, you got to admit that this wouldn't have taken that long to do. And then if I come over here, I get it into polar form. And when I get into polar form, I have my solution. So if you were really practiced, you got to ask yourself, could you have done this really quickly? Would this have taken you longer to do with the differential equation, or would it have taken longer to do with the Phasor solution? I would say that it would take a hell of a lot longer to do it with the differential equation. This is a real shortcut here. Yes, sir.
What you have is IS, are you dividing one both by Z?
Yeah, with these guys right here, I define these.
So does the Z equal 1 over Z to the negative J?
So is this negative?
No.
Yeah, when I bring it up, I agree, I got a negative sign.
No, I mean, should be one vote times Z e to the J theta. The Z could equal 1 over Z.
This guy right here? What's wrong with this? Is this what you're talking about?
Yeah.
I think that's okay. Right, that's just the definition of this guy. Yeah, I think that's okay. I don't think I did anything incorrect with it. Yes, sir.
What happened to the sine term in the real function?
This sine term right here? Oh, because I'm only looking at the real part.
Okay, I see.
The imaginary part's still there.
Yeah.
And it plays a different role if we were looking at sine. But as far as the differential equation, that's the solution right here.
Okay.
Let me see if I could stomach one more circuit, or if you could stomach one more circuit, because, you know, it might be cocktail hour after this one, right? Okay? So let me see if I can move through this one. And remember, I'm not so much interested in the details of getting bogged down. I just want you to look at the circuit and go like, okay, I know what to do. I agree, it's a bitch of a process, but at least I know what to do. Okay? So let's do this again here. So you know what? I'm not even going to go and interpret this, right? Because I would love to spend some time telling you what this all means. Which is really too bad. Okay, can I erase this? Okay, last example. Let's see, what example do we want to do next? Okay, here's the next circuit. So what we want to do here is that we want to look at this circuit. And right, you're kind of, you might be laughing at this, but let me ask you. Would you like to solve this as a differential equation? Yeah. All right. That's 1, 2, 3, 4. But in phasor form, you'll see we'll do quick work to it. Okay. So let's start all the way over there. Let's do that. So we're on this example. And when you look at this guy, we got 10 cosine of 4t plus 63. And I have this mess right there. And what we're looking for is that we're looking for this voltage across that inductor right there. So the thing that I would ask you here, don't think about phasor form, okay? Don't think about phasor form, phasor form, but in this, how would you solve for the voltage of this inductor right there? You could do KVL. I would use a voltage divider. Because one of the things that you'll see here is that, note, this is going to be a phasor all by itself. Okay? That's going to be in complex form. Note, when I add that this will have a real part and an imaginary part, but wouldn't you agree that this branch and this branch must have the same voltage? So if I calculate the voltage across this drop here, It has to be the same as the inductor voltage drop. So what am I going to do? I'm going to set up 2 blocks. So the way I'm going to look at this guy here is that I'm going to say, here's block number 1, which I'll call Z1. Here's block number 2, which I'll call Z2. And then, in the end, I'm going to have some voltage here, and I'm going to have some voltage source here. Then I'm going to use VDR. What does VDR tell me to do here? It says that if I want the voltage across the second term, it's got to be Z2, Z1, plus Z2, V source. Are those all vectors? Absolutely. But, you gotta admit, I agree that the algebra, I mean, it's not pretty. But you gotta admit, at least you know what to do here. Right? We're just gonna walk through this thing. So what am I gonna do? I'm gonna go calculate Z1, Z2, and I'm gonna do that. And here's where the calculator is just phenomenal. So what would I probably do? I'd probably set, see, I would probably put this into, I'll put this into polar form. This guy, if you have a calculator that adds it, you would add this in polar form with this guy. You would literally punch into your calculator the polar forms, and then, I love the 89. It just does it very nicely. In the 83 and the 84, you do pretty well too. It's when you get to complex matrices that it becomes a problem. So here we go. Let's go calculate C1. Okay? Let's go calculate C1. So if I look at C1, what do I have here? I have this guy. Right? So I get, is it 2.5 Henry? I think that's what I have. 20, and then this is 10 millifarads. So if I start to do this here, what I'm seeing here is that I'm going to look at the 10 millifarad. Right? That's the capacitance. So then that means here I got to write what? Omega C. What's omega? Omega's 4. So I'm going to get what? I'm going to get 4 times 10 milli. Right? I get 10 milli. And if I do that, I should get up what? I'm going to get 10 to the negative 2. 10 to the 2 is 100. 100 divided by 4 is 25. So I'm going to get 25 ohms. Okay? And if I look at the inductor, this guy here, it's got to be omega L. So if I look at this guy here, it's got to be what? It's got to be omega is 4 times 2.5, which should give me 10. Am I always going to give you nice numbers like that? Absolutely. I will try to give you the nicest possible numbers that I can give you. Okay? So then if I put this together now I want to calculate C1. Okay? Let's calculate C1. So note that I got to add these guys. So this guy must be parallel to this. So it's got to be what? This guy is then really what? This guy is the same as J, 10 ohms. This one here is minus J, 25. So, there I go. So I go, these guys are in parallel, so it's got to be this times that. So it's got to be 20 minus J, 25 times J, 10. Divided by the sum of these two. And to divide that by the sum of these guys, it should be 20 minus J, 25 plus J, 10. Now, if you clean this up, if I start to multiply this guy out here, you can see that I have minus J times J gives me 250. J times 20 here, 10 times 20 gives me 200. So I'm really getting 250 minus J 200. That's what the numerator is. The denominator is that you can see that I get minus 25 plus 10 gives me negative 15. So this should be 20 minus J 15. Assuming that I have a good answer to this.
Shouldn't it be plus 200J? Shouldn't it be plus 200J?
Should it be, where should it
In
be
the
close?
numerator, because it's 10J
Yes,
times 20.
thank you very much, you're absolutely correct. So then if I clean this guy up here, I'm just going to say, assuming that I get the right number here, because if that's a minus sign, I probably have a minus sign in my answer. So I don't know if I screwed up when I was typing it out, but I ended up getting this into polar form. So what did I do? I put that into polar form, I put that into polar form, or I just punch it into your damn calculator. You punch it into your calculator, I got 1281 with an angle of 75.5 degrees. That's what Z1 is. I got Z1 to be that in polar form. Now remember, I'm only doing this on the board so that you could sort of like see my process of how I deal with things series in parallel. If I had this in my calculator, if I had a calculator in my hand, I never would have done this. I would have written it like this, and then I would have gone right there. That's what I would have done. So now let's look at Z2. So if I look at Z2, let me draw it over here. Z2 then has this guy. And so in this case here, this is what? 5 Henry, this is 40, and this is 5 million. So I almost never do these in my head unless it's like super obvious. I always try to do these in my head. Okay? So let's look at XL. So if I look at XL, it's got to be this. So we know that the frequency is what? 4? 4 times 5 is 20. 20 ohms. So I would have done this in my head and I would have said J20. Now let's look at the capacitor. The capacitor, XC here, has to be what? It's got to be 4 times 5 times 10 to the negative 3. If I bring this guy up, it's 1,000. 1,000 divided by 20, is that 50? I think so. Right? You're supposed to agree at this point. Okay, good. So now we're moving on here. We know that this guy has to be minus J50. Right? That is right, right? 1,000 divided by 20 has to be 50. Okay, so now, let me tell you what I would do with my calculator. I put it in rectangular form, complex form, right? I write Z2, here's what I would do. It's got to be what? This times this divided by the sum. So on paper I'd go this times this, so I'd go J20, and then I'd have 40 minus J50 divided by the sum. So the sum of these guys, look at that, that's got to be 40. And then look, I got to add these two. If that's negative 50, it's got to end up negative 30. And then what do? In my calculator, I do, in this rectangular form in complex, I go this times this divided by that. And by the way, I have links on my page that show you how to do this on your calculator. So when I calculate this guy, I ended up getting 25.61 with an angle of 75.5. Damn, I hope that angle's right. So? Yes?
Is that 40 minus J30 or 50?
See, I got to sum these two. Minus J50 plus J20 gives me minus J30. So now, what am I going to do? I'm going to use voltage divider rule, right? Like we did over there. So what's the voltage of the inductor? right? The voltage of, what was it? 5 Henry. The voltage of the 5 Henry has to be what? Z2, Z1, Z2 times the source. Now we didn't convert the source here, but look at the source here. Look at that phase. When I go to a phasor circuit, this guy has to be what? 10 with a phase of 60 degrees. Times the source here. So then I have my polar forms here. So here is where, you got to get a little bit savvy. So now I put this in polar form now, right? So this is 1281. You know what? I think that answer right there is yes. Right? There's no way that angle could be the same as that. I know I screwed up someplace. Since you don't know what the hell I'm doing, let's just keep going on. Right? So if I do this, right, there's nope, I'm supposed to do 25.61. And then I'm going to do, then I add 12.81, 75.5, plus this 25.61, 75.5. And here's where the tricky thing is, with an angle of 60 here, is that now you pop into polar form. And if you pop into polar form, I can add these two numbers together. So I literally, in polar form, plug this guy in, and then I divide, and then I put my parentheses, and I add that one plus that one, and then I get this term right here, and then I just multiply it like this in polar form. And yeah, this angle's bothering me, but we're just going to say that it's right, which I don't believe. And then I get this answer of 60 degrees right here. Wow. No. Okay? Yes, sir.
Okay, well, the elements in group 2 are basically the elements in group 1, but with twice the reactants, right?
Sure.
So,
But then I could say that,
well, in that case, it makes sense that the angle would be the same for each.
that's what I calculated. It just makes me very nervous. So here, there's the phasor voltage right there. So by the way, if you wanted to go solve the differential equation, what's the solution? Look how sweet this is. So now, if you want to go to the time domain, what do? It's got to be what here? Look at the voltage across the 5 Henry as a function of time. What's the amplitude of this dude? Look at this. And then I get cosine, and I go, wait a minute, there's an angle here. Right? Or a phase, this guy starts off at what? 4t here, and then the phase here is 60 degrees, and that's that. You gotta admit, that is an impressive thing that you can actually mathematically go from here to there. I think we should go this, yes.
When you're calculating the phase angle, or when you're still in polar form, it's technically an exponent, right?
It's an exponent.
Yeah, so you do the 75 minus the sum of the other 75.
Yeah. And so in this case, they would cancel out.
Yeah.
And that's why it's no surprise that that angle and that angle are the same. I'm just saying that the fact that I got the same angles makes me a little bit nervous.
Yeah.
Okay. How about if we stop here? So tomorrow, I'm just going to review for the final exam. I'll come in with the practice exam. We just gonna go straight right through it. Yes, eight. Eight upstairs, yes. Okay? Hey, thank you for coming. Sorry.